So welcome everyone to the Matrix International Forum. The forum is organized by the Meta Research Innovation Center at Stanford, or short Matrix. The center is directed by John Ioannidis and Steve Goodman, and we are a research group and fellowship program dedicated to finding ways to improve the validity and transparency of scientific research. I'm Max Siebert, a postdoc at Matrix, and I will be today's moderator. All of our international forums are recorded and can be accessed on our website or on YouTube. Please keep your questions until the end or write them in the chat during the presentation. Our presenter today is Matthew Sigurdson. Matthew is a doctoral student at Stanford University, advised by John Ioannidis. Recently, he has successfully defended his doctoral thesis on the topic of null fields, with graduation expected in fall 2024. Previously, he also received a master's degree in biochemistry from Stanford. His research interests include the study of bias in the scientific literature and methods for mitigating its effects. So if you're ready, Matthew, we can start.
Great. Hi, everyone, and thank you for inviting me to be here. Welcome to my presentation on the topic of null fields. Some of you may recall that I previously presented this at Metrics back when it was just a project proposal, and I got a lot of good feedback from the meeting. And as Max mentioned, I recently have gone through to defending my thesis on this topic, and now today I'll be presenting the results. So I've titled the presentation "Using Null Fields to Quantify Overall Bias in the Scientific Literature." Now, by null fields, I mean a field of research that attempts to study a non-existent phenomenon. So historical examples of this are N-rays, cold fusion, and many other things. And this sort of thing can arise from multiple sources. For example, one way to categorize this might be whether they're determined based on existing knowledge to be null, or if they're initially legitimate research that is just later shown to be incorrect. And we could call that a priori versus a posteriori null fields. The key thing, though, is that these fields are trying to measure an effect when none exists. And this can be extremely valuable in the analysis of the scientific literature because it's potentially a method to correct for bias. And this is a critically important topic when we want to improve the effectiveness of scientific research and the rate of scientific progress. Now, to motivate what I'm referring to by this, one of the primary methods we know to address bias is to introduce a control group. And scientific experiments do regularly include controls. But this is insufficient because if we step back and look at the level of a field of research as a whole, bias still remains. It can be very difficult to find a useful control at this level. But if you ask what a control group would look like in this context, you might imagine something like people running scientific experiments, publishing in the scientific literature, acting like they're doing good science, even believing that they're doing good science, and so forth. But they're studying something that doesn't exist, something where the effect size is 0. And it turns out that this is an excellent description of a null field. This isn't something you could set up, but it occurs naturally. And as a result, null fields can be used as negative controls for the entire process of science. Since no true effects are present, when you have no bias, the average observed effect size is null, whereas if there is bias, then your average effect size is different from null. So observed effects are direct measurements of overall bias. Another way to frame this is when you do a study, results are typically compared to the measurement representing no effect, the null measurement, for example, odds ratio of 1. However, a more appropriate measurement is to make a comparison to the expected level of bias. And the most appropriate control group may be to compare to a null field. Null fields provide an estimate of the total bias present across all possible types of bias. This is something that meta-analysis cannot do on its own, since that is directly based on the results reported in the literature and that incorporates many types of bias. This is sometimes referred to as garbage in, garbage out. Beyond meta-analysis, most other bias correction methods focus on individual types of bias. And this is valuable for analysis, but if you want to determine the accuracy of your experimental measurements, the estimates of total bias are always more important. And if you try to correct for many biases individually, you encounter issues like whether all sources of bias can even be identified, whether specific bias correction methods are applicable to estimates that are already correct for other biases, whether these biases are mutually exclusive or overlap with each other, and cumulative error from performing many different estimates of bias that all have their own uncertainties. And null fields avoid issues from these types of issues. Another advantage of using null fields is that just like the concept of negative controls in general, using null fields is not dependent on specific measures of specific methods of comparison. So for example, they could be used for empirical calibration, taking an effect size based on regular significance testing and then applying a correction factor based on the expected degree of bias. But they could also be used in Bayesian analyses, either to develop priors or to affect the calculation of posterior probability. And conceptually, the idea of null fields still applies with only minimal adaptation required. Similarly, the use of null fields is generally compatible with other methods of bias correction. So if better methods are available in a specific situation, then an appropriate null field control, one where the same methods were used, can be applied afterwards, and then that will cover all sources of bias that are not already addressed by existing methods. And then finally, null fields can also teach us about bias more generally. So for example, since the underlying effect is exactly zero, we know exactly how far any result is from the truth. We can measure bias precisely in the absence of any complications caused by actual effects. And as a primary example of a null field, homeopathy, which includes the claim that smaller amounts of treatment make remedies more potent instead of less, so reversing the concept of dose response. And generally, this involves performing serial dilutions to the point of using pure water. And well, for this to work would violate well-known physical laws. And the point is that all scientific evidence, as well as a priori reasoning, suggests that this is a null field. Hypothetically, one can claim that homeopathy is effective regardless, and then that would prevent the use of homeopathy for this purpose. But this doesn't affect the general concept of null fields, only which fields you accept as negative controls. In this case, homeopathy is an ideal example because in addition to the high certainty that it's null, the specific way that it's null is that it's literally the use of placebo pills. It's the comparison of placebo to placebo. And this makes evaluation very simple. There's no chance of complications due to side effects and so on. And now the current status of this project is that we picked homeopathy as the first null field to be analyzed, and that's been published in Journal of Clinical Epidemiology. And we have also done energy medicine, which is currently being prepared for submission. Now, the research pipeline has a number of unique challenges associated with it. The methodology needs to efficiently collect the necessary data in a consistent manner across multiple fields of research, not just homeopathy, and also not just null fields, but eventually also positive control fields and any other field that we may be interested in performing comparisons for. And this all has to be considered from the beginning to allow these comparisons to be made. And so I have a list here of the key challenges, which are ensuring that the protocol can be expanded systematically to multiple fields, including fields that are either narrowly or broadly defined, as long as enough studies are available. Providing a method to define the scope of a field using objective criteria so that the set of studies where the pipeline can be applied it can always be precisely determined. determining what data is likely to be useful across many different types of fields and many different types of analyses, promoting consistency in data abstraction across multiple fields. That involves ensuring that variables are defined comprehensively and minimizing subjective aspects of data abstraction, even if, for example, I'm collecting the data at very different points in time. Then maximizing the efficiency of data collection, since this has to be applied multiple times, and avoiding reliance of the protocol on any field-specific characteristics. And designing and applying this protocol has been a major part of my thesis, followed by evaluating its effectiveness and working on streamlining the process. And as an additional benefit, the pipeline also applies generally to a large category of different applications with only minor modifications. But now a large part of the answer to these challenges is to do things automatically. So, for example, wherever possible, I've written code that collects the data automatically, for example, through direct code-based queries to PubMed and other databases. Now, this is the summarized procedure for identifying papers and retrieving the variables while accounting for the challenges that I've mentioned. So the scope of the field is defined using papers that have been included in meta-analyses. And this allows a more objective paper selection algorithm, which means we're selecting higher quality papers and reflects analyses that have been selected by the researchers who study the field in question. And given the initial search terms, the algorithm is that we retrieve meta-analyses. That is to say, there's three categories: umbrella reviews, Cochrane reviews, and papers that are tagged as meta-analyses in PubMed. We then order them by number of citations per year, so prioritizing those that are highly cited. We identify the papers used in each meta-analysis, and then select the individual papers up to the desired quantity. And the only step in this that has to be done manually is identifying the papers from each meta-analysis. Everything else is done by the code, other than, well, we have to input the search terms that we were interested in at the very beginning. Any meta-analysis published in English and indexed in PubMed, while full text accessible, is eligible for the analysis. And the greatest amount of effort in the data collection is in evaluating the effect size, in part because that's the most important as the primary outcome variable. And to resolve the challenges mentioned previously, the protocol has to be precisely defined and produce a result for a very wide variety of inputs, including not only different measurements, but also all the differences in what the authors may or may not have reported, and what statistical tests they have performed, and so on. And each paper does have to be evaluated manually for this. I developed a full procedure to select which variable will be evaluated, regardless of how the paper has been written or what information has been included. Some of it still can be automated. Once the specific information is entered in the spreadsheet, regardless of what exactly that information is, the code evaluates it and converts it into standardized mean deviation, specifically HGG, and odds ratios, and also accounts for the directionality of the measurement and all the other factors that are relevant to the result. So this maximizes consistency, minimizes the chance for error, and so forth. All the data retrieval is done automatically or partially automatically where possible. And when I say partially automatically, I mean something like the effect sizes, where the evaluation is done manually, but calculations are done automatically. Another example of that would be the creation of reference data sets, where the code can refer to those files when creating the main data set. There are a lot of variables retrieved, since a lot of the relevant analyses are exploratory. In general, I'm interested in any variable that is potentially related to null fields. I also have several functions that are used to support the analysis process for the same reasons, including data processing, but also production of summary statistics, evaluation of correlations, and univariate analyses. Now, this is the same thing in the form of a flowchart using the numbers from our analysis of homeopathy. It's a modification of the one that we published for the homeopathy paper, switched into two columns to fit on the slide, and also some simplifications for ease of reading. In homeopathy, we found 63 unique meta-analyses, and starting from the most highly cited, we took at most 10 papers per meta-analysis until we reached our target of 50 papers, and then we went on to perform the analysis. So Firstly, general observations of the data set. All the papers we retrieved were clinical trials, randomized controlled and placebo-controlled, published between 1983 and 2010. This is in part due to the paper selection algorithm, which requires prior publication in a meta-analysis, and also in part due to when the influential meta-analyses in this field were published. Some of them were quite good journals. Out of the sample of 50 papers, we have 3 in Lancet and 3 in BMJ. On the other hand, some are in very poor journals as well. That is to say, journals with no impact factor, which are not Medline indexed, and so on. And the expected results, of course, if there's no bias, are 2.5% in either direction. So either 1 or 2 studies out of the 50, and that's just based on the nature of p-values. But the actual results after recalculation, by which I mean errors have been corrected and so forth, the actual results are that 17 of the studies favored treatment at p less than 0.05 in their primary outcome variable. And if we consider only directionality, ignoring significance, we have 40 studies favoring treatment, 9 favoring control, and 1 being exactly 0, instead of being half and half like we'd expect if there's no bias. This is a histogram of the effect sizes as the primary outcome variable. Since this is a null field, we expect the mean value should be 0. But our result is that we have standardized mean deviation, Hedges G, of 0.36 standard deviations. This also corresponds to an odds ratio of 1.94, or if you are looking at something in the other direction, the reciprocal is 0.52. This represents an estimate of the total amount of bias present in the field across all possible forms of bias. Or in other words, if you're measuring an odds ratio, a measurement of 1.94 might just correspond to a null result. Now, of course, in any individual case, the actual amount of bias present may be different. But following the idea of using this as a negative control, the idea is that we want the best available estimate in the absence of additional information. And, well, at minimum, this is better than the current default, which is to assume that there is no bias at all. Now, for this paper, we also did a number of descriptive analyses, which I'll address later. But first, a digression, since our paper received a lot of attention. It's now about 16 months since publication, and we already have 9 citations recorded in Scopus. One of these records is from a group that has already done a follow-up analysis on our data set. That's the image in the top right. And since we made all our data publicly available, the authors were able to reuse our data with a focus on the impact of publication bias in the literature. Another reference is an editorial in the journal Evidence-Based Practice. That's the second one in the top right, where the editor basically said that from now on, he might use our results as a benchmark when he's reviewing papers. In addition, beyond the direct citations, we also have a very high altmetric attention score. That's 144, which is 98th and 99th percentile across the 4 categories shown here, including the #1 position for publications of similar age from Journal of Clinical Epidemiology. So this has generated a lot of interest in other contexts as well. As some examples, we have a very positive blog post by Edzard Ernst, one of the top experts in this, and also a news article, a magazine article, and a podcast. This is all across multiple languages, so as well. So so far, other than English, the main examples are Norwegian, Dutch, Italian, and Japanese. Of course, some people do believe that homeopathy works. One of the citations is an editorial in the Homeopathy Journal, which appears that it's supposed to be a conference report, but it's 16 paragraphs long, and roughly 7.5 paragraphs were spent on attempting to criticize our paper. Another is a response which argued that visiting a homeopath may have psychological benefits. That's the second one. And there's several issues with this, but one is that it isn't actually relevant to our analysis since we're analyzing the effects for the treatment and not incidental effects that one would expect to be removed by the use of appropriate control groups. I included these quotes in my presentation because one of my professors insisted that I provide them as really amusing examples of flowery writing. So only time will tell how much positive evidence is required to break through our positivity bias blinkers, and we should not expel homeopathy to graze in fields of nullity. But it is worth restating that our analysis does require you to agree with the premise. Our analysis isn't about arguing that homeopathy is a null field, which is exceptionally well established already, but is rather following up on that fact to study its implications. So, moving on from that, an important aspect of my project is to study multiple examples of null fields, with the second example we chose being energy medicine. This is a category of treatments which generally claims to manipulate energy fields for which no evidence exists. And there's generally no direct contact with patients, and so no possible causal pathway for the claimed effects to occur. There can still be interactions between the practitioner and patient, even though that could theoretically have effects, but the idea is that these aren't part of the alleged treatment, and so they would be canceled out by any study that's properly controlled. Now, not all types of energy medicine actually fall into this definition that I've provided here, and those others are excluded. So, for example, some of the types of energy medicine claim to be manipulating magnetic fields, and of course, those do in fact exist. But for this purpose, I left them out since the goal here is to evaluate fields where the status of being null is as indisputable as possible. Thus, the focus on there being no possible causal pathway. And so for energy medicine, ultimately, we're focused on two specific types, which are Reiki and therapeutic touch. These were chosen based on the available studies. There's 18 Reiki and 34 therapeutic touch. These are the two subfields with the most studies available, and the accommodation results in 52 total, which works well since the goal is 50 studies to be comparable to homeopathy. Now, in these two types of treatments, the practitioner's hands are placed at positions on or in the patient's alleged energy field and then held there for various lengths of time. And the treatments are essentially identical based on the actions being performed. So as with homeopathy, they are effectively placebo treatments with no possible beneficial or harmful effects. Now, general observations, n equals 51, which is one less than the total number of studies since one didn't have a valid effect size. In these studies, the quality is generally even worse than homeopathy. So this is referring to blinding, sample size, lack of primary outcome variable specified, methods not being described, and so on. We have 44 of them being randomized controlled trials and only 20 being placebo-controlled randomized controlled trials, in contrast to homeopathy, which had all 50 being placebo-controlled RCTs. And most of these were in low-impact journals. We didn't have any examples of high impact like for homeopathy. Now, so following a similar analysis to homeopathy, we expect, if there's no bias, 2.5% of studies to be significant in either direction. But the actual results, instead of 1 or 2, we have 16 studies that favor treatment at p less than 0.05 in their primary outcome variable. Or if you specify only direction, that's 43 studies favoring treatment, 7 favoring control, where 1 was exactly 0. Our mean effect size for placebo-controlled randomized controlled trials is 0.42 standard deviations, whereas with all RCTs, you see an even higher degree of bias, 0.5 standard deviations. The histogram here is displaying the results for RCTs generally. And so these two numbers correspond to odds ratios of 2.19 and 2.55, respectively. And so comparing the placebo-controlled number, 0.42, to homeopathy, we can see this is a very similar result. And so if we combine the two samples, so the total of n equals 70, the overall estimate is 0.38 standard deviations, or odds ratio of 2.01. So this is the most updated current estimate that we have for the effect size that is expected in a null field for placebo-controlled RCTs. I also have a number of other variables that I've been looking into, and some of these are presented here with a focus on those related to study quality. These ones are the numbers for homeopathy and energy medicine combined. I'll get to the comparison later. I'm looking specifically at RCTs, so we have 50 from homeopathy and 45 from energy medicine. So we can see that we usually have a subjective primary outcome variable. We usually do not have a pre-study power calculation. We usually do not meet adequate standards of randomization, and so on. With regards to that last point, adequate standards of randomization is a set of requirements based on the consort criteria, evaluating generation of the allocation sequence and the methods of allocation concealment. Another variable that might not be clear from the description is valid main effect reported in primary conclusion. This is defined with a number of specific criteria, but it's effectively asking, given the numbers reported in the study, does the primary conclusion of the study include a meaningful and correctly performed comparison based on those numbers? And as you can see, it's quite common for this criterion to be failed. We have 53 successes out of 95. So in general, you can see that the studies in the sample don't do too well. Although there is one case where things aren't as bad as they could be, so that's specifically subgroup analyses. You can see there's 30 papers that include at least one subgroup analysis, but actually most of them didn't actually affect the conclusions of the studies. So for example, in these fields, when the authors spin the results of a study, they didn't often use subgroups to do so. Now, speaking of spinning of results, if papers didn't have an analysis that supported the treatment, more than half of these papers went on to spin the results favorably regardless. And specifically, the number is 39 out of 70 papers that described the analysis positively in their main conclusion, despite that not being supported by the primary analysis. Whereas the remaining papers did present numbers that supported the treatment. So the methods of spinning would include things like emphasizing trends, performing within group comparisons, and so on. In addition, we identified a lot of errors in the papers. This first line, within group versus between group errors, means that they used a within group comparison to draw between group conclusions, or they failed to report a between group measurement in the first place. Now, this list of errors is not exhaustive, meaning these are the only 3 categories of errors evaluated. We didn't look at, we didn't record other types of errors. And furthermore, they're only counted if they're absolutely unambiguous. So for example, math errors are only included when it was entirely impossible for the numbers that they were reporting to be consistent with each other. And of course, these numbers don't add up to the total because many of the errors overlap. We also did a Spearman's correlation analysis for homeopathy, looking at variables which were associated with either effect size, significance, or positive descriptions by the authors. And most of the correlated variables that we found relate to the number of citations received. After correction for multiple testing, there were 3 associations that remained with 3 variables that were associated with at least one of the index variables. These are the number of citations from high-quality journals indicated by indexing in the directory of open access journals, the number of citations from questionable journals indicated by the Wikipedia SiteWatch, and the presence of a demographics table describing the sample characteristics. We did this analysis for energy medicine as well, but in that case, the results were mostly non-significant. Now, finally, we looked at comparisons between the two null fields. For this, I ran univariate analyses across all the variables collected, and these are the results ordered by significance after correction for multiple testing. The ones reported as percentages are fractions of the total, while the rest are means. And you can see, well, the top result is double blinding. We can infer that the difference is due to greater difficulty in actually blinding the practitioners, although there is a result as for single blinding as well, for which that isn't a valid reason. Other than that, we see that homeopathy studies are more likely to identify a primary outcome variable. Energy medicine studies are more likely to cite more references. Homeopathy studies are more likely to have more authors on their papers, and so on. All that said, as I mentioned earlier, the average effect size was very similar for the two fields for placebo-controlled RCTs. So in other words, it seems that the relatively higher quality in homeopathy studies does not translate to a notable reduction in the total bias. And it could be that this is due to uncertainty in the estimates, but it could also be that the improvements are simply window dressing for otherwise predetermined conclusions and don't represent actually doing better science. Now, for the future, in addition to further refinement of the research pipeline, the idea is to characterize additional fields. So that would include different types of null fields. That would be to improve on the current results and also to provide additional reference points, since different null fields may be the most appropriate control in different circumstances. Then there would also be positive controls, fields that are well known to have substantial effects, and then everything in between. The next stage then is putting into practice the use of null fields as negative controls with comparisons across multiple fields across a broad range of degrees of expected legitimacy. The idea is that we can identify differences between fields, identify factors associated with null fields, identify possible indicators of null fields, and so on. Now, in general, these types of comparisons are often complicated by the great diversity between fields. Ideally, we could identify the most productive and valuable fields and then determine what makes them successful and then replicate that across all of science. Now, a key challenge with that approach is that, well, even though it's often recognized that fields of research are not all equally successful, we don't actually have a widely applicable measurement for success. However, the characterization and analysis of null fields is a crucial step forward in this regard because these are fields that are definitely unsuccessful. Ultimately, we might possibly even be able to identify null fields that are not yet recognized as null. So thank you very much for listening to my presentation, and I am happy to take questions.